Okay, so now we know who we are. So I'll tell you what is ahead of us. So our tutorial will teach you how to run your image processing macros and scripts remotely on high performance computing infrastructure and try to fully utilize its parallel capabilities. So we have prepared a set of tools with graphical interface that we will be working with. It's fully integrated into the Fiji, so we'd like to make it as easy as possible. And we will show you how to use them. But just maybe before, you may ask why, because why to make it so complicated? And I think the reason is obvious. The data are getting bigger and bigger, and it's harder and harder to process them on a single computer. Just to give you one of our examples, we have been processing the SPIM data on a supercomputer, and it took approximately 13 hours. But normally, if I would run it even on a single high-end computer, so basically then I would have to wait for more than a week to get the same result as I had during the day. The plugin that we have developed and you will be working with is built upon a standard message passing interface, which is a dominant model still used in HPC world. And we choose it because it is so common that we may say almost for sure that it will be available on any supercomputer. So basically, don't worry that what we will see here is not applicable for your supercomputer. So we can say almost for sure that you should be able to run it. And we are here basically to help you to even install it on your computer. We have already successfully deployed it, of course, in Ostrava and also on Max Planck cluster. And if you would like to have running this on your supercomputer, so just don't hesitate, contact us, and we will show you how to do this, or we will even help you basically to install it and have this installation running. For this specific session, we have granted you the access to one of the IT4I supercomputer called Salomon. And when it was launched in 2015, it was number 40 in top 500 supercomputer rankings. So the 40 fastest supercomputer in the world. Of course, after the years, many new supercomputers appeared. And if I've looked in the table just a few days before, and it was on 460 place, but still it's ranked in top 500. So let me show to you where is this supercomputer located. So this is the building of IT4I Innovation. It's in Ostrava in Czech Republic. So it's the Europe. We are in the basically heart of the Europe, and Ostrava is located on a east part of the Czech Republic. And the building you see, so in this building, your code will run just in a few minutes or during the session. So you can imagine that basically your code will just run inside the building in Ostrava. And if you go inside, so basically you can enter, or basically you will not normally enter this room, but this is the room of the supercomputers. And currently we have 3 of them already installed. Their name is Anson, Salmon, and Barbara. And there is also a 4th one, a new one, which is now being installed. But unfortunately, we do not know its name so far because it will be publicly announced in a few weeks. And the computer that we will be working with, the Salomon, is the largest one. And maybe you might have been a little bit confused with the emails we have sent you in advance, namely with that obfuscated passport. But it was the only option, because the reason for this is that the access to supercomputer is, let's say, heavily guarded. Supercomputers are considered as a critical infrastructure, so its computation time is extremely expensive, and the storages hold many valuable information. So I think it's clear now why the security and the data confidentiality are basically the priorities for our staff. And on most the supercomputer, it is also not allowed to use the normal logins with the password. So basically you need that private key that you should have already downloaded in advance. There are many reasons for this, but basically the passwords are not considered as a super secure. It can be easily hacked. So if you attempt to connect to most of the supercomputer centers, the procedure will be quite similar. And even if you do this on real, so basically they will ask you to somehow prove that you are who are saying, so basically some ID or some certificates and so on. So this is the normal way how to obtain the credentials, but somehow we managed to send it through email, but with that obfuscated way that you have already, I hope, successfully managed to decode. So let's have a look at the session outline. I told you that there will be basically, let's say, 2 sessions interrupted with some intro and more in-depth look. So if we start with the first one, which will take approximately 2.5 hours, and don't worry, we will make a break, so it will not be a 4-hour run. So in that first part, we will teach you how to use our plugin for remote execution of macro script on remote supercomputer. So that the macro will not run on your computer, but it will be transferred to the supercomputer and run there. And Vlado, during that time, will show you some hints how to parallelize your code to run efficiently. So to be, let's say, more specific, the scenario we are targeting by this part may look like this. You have locally a lot of images and some macro or script to process them. But unfortunately, there are so many data that is basically overwhelm your computer for a long time if you try to process them locally. So you usually don't want to get stuck and wait for long hours. So what we will teach you and what we will do is how to upload the data and the macro to the supercomputer. There, we will teach you how to write a macro, so, or the script that basically will divide your data into small groups. These groups will be processed by individual nodes, so they have less job and there are more of them. So basically it will take definitely shorter time than if you do this just on a single computer. And when this calculation, that image processing will be done, so then you will see how to download them back to your computer and basically use the results that you have obtained this way. So this will be the first part. It's mainly the introductory. It's for beginners, and Vlado's intros will be for a little bit experienced user. We will try to teach you how to parallelize your code. And then, let's say at the end of the session, we will also show you some more advanced feature. So this is a little bit different scenario. It's involving Imagej ops, and this will involve the jobs that are set or they are not so embarrassingly parallel as the previous one, because on the previous one, you can simply divide the files and process them independently. But if you have some super large image that you would like to process, it's just one file, so you cannot divide it somehow some easily on file system or copy just the file. So what will you see is again how to upload the image to the supercomputer. But there, as I said before, the data cannot be split so easily. So it must be done in more clever way. So basically, you can imagine that the data will be cut like to a jigsaw pieces, and each node will be assigned to an individual node. So each node will just compute that stuff or that program algorithm you have in your script or macro on that small piece. And later on, when these small pieces are processed, so then they will be put together and send back to your computer. So then you can download again that huge image, but now processed by the supercomputer. So this is basically what is ahead of you. And because it's everything new for us and also for you, so it's quite important to give us the feedback. So don't hesitate to use all these Zoom functions. So basically, if we have some problems, write to the chat. So The Pavel will help you if you have some problem with accessing the keys. Vlado will help you if you have some problems with the Fiji or some strange errors may appear. So just use them as possible. And also, just to be sure that you are still on track with us, so we have put after each session a small questionnaire. So it will be like that, milestone that you have successfully finished. So the screen or that small page you've seen, it is the page that you have the link in your email. So, okay, once more, this is the email that we have sent to you, and there was this link. This will most of the material that will be covered. And if you click on that link, it will guide you to this wiki page. And here you can see there's the outline of our presentation, and there are the pictures and how to do this. And after each of this step, or let's say the part, there is that small red flag. And if you click on this, it will point you to that small questionnaire. So basically, there just fill your username and give us the feedback if you completed successfully. I will have a look at it during the time. So if you have problems, we will notice it. We will stop and try to fix it. And also just indicate if it was easy for you, so you already know it, or if it was hard. So I'll just select 2 and submit it. So this is the job that you should do after finishing each of the steps of the presentation. And we will also ask you to do this. And if I go back to the presentation, so this will be during our tutorial. And after this, so remember there is that beautiful island. There is a great video of Pavel. So be sure to see that there are some special times to it. And we have also there the hut. So you see me there right now standing and waiting for you just to discuss all your problems and exciting research that you are doing. And we will try to help you. There is also the Slack channel. So if you didn't do this in advance, so just have a look at the channel, which is dedicated to our sessions, that bridging Fiji and OpenMPI. We already put there some, let's say, almost crucial information for the Mac users from the previous session. So join it. Basically, if you are in the Slack, so there's that button Add Channel. It will show you that browse all channels, and in that list, we are one of the first. So just select that bridging the Fiji and OpenMPI, and here we can discuss it. And as I understood from the other conversation, basically the Slack will remain there, so you can contact us even after that conference, and we can try to find out how to help you and how to speed up your macros. And we will also make that break, but I will announce it a little bit later. So that's all for me for that, let's say, the introductory part. So if you have any questions, just feel free to ask. And if there are no questions, basically I can check it also in that questionnaire. So we will just continue with the Stefanos and the first part, basically covering how to install everything and set up, so you will run your code here in Ostrava. So time for questions. And none are heard. I think in conversation there is nothing. So Stefanos, Zoom is yours.
Okay, welcome to Bridging Fiji and OpenMPI for easy to use parallel processing of images. This is the first part of the workshop, and our goals for this part will be these. The first one is gaining access to the remote HPC. This is the one that was in the prerequisites in the email, and you should now have the username, password, and the key file. And then we will proceed to installation, configuration of the plugin, upload, running and downloading macros remotely, and monitoring progress, output, and error reporting. This part is meant to make you familiar with the graphical user interface of our client plugin, which we'll be using to access the high-performance computing cluster remotely. And then we will proceed into these three goals, which are to familiarize you with writing, with parallelizing your microscripts, and we will see a parallelization of a microscript, how to use and report progress with the progress reporting functions, and the demonstration, finally a demonstration of a real parallel macro. After that, there is the presentation by Daniel and a small example related to this. So let's start by explaining the workshop structure. Each part of the workshop is hands-on. You are to participate in this. Please follow along, and there will be worksheets. The workshop is organized in worksheets, and we will be following each one of these. The link is in the email that Michal reminded you of. In the link, if you follow this link, it will lead to this central hub in this wiki page for this workshop. So our first step is to first provide the feedback on the prerequisite steps. So there are two steps which you should have already done, which are to download Fiji, install it, and get the username, password, and the key file. So at this point, I would like you to fill out this, to click on this red flag and fill out the form. I'm going to fill it out as well. Please indicate here whether you have completed these prerequisite steps, or if you have any issue, any problem during this step, please select no so that we can help you with this task. And press submit, and I'm going to wait now for Michal to collect the responses.
Yeah, so far it looks that the users are fine. So we have Camille, Livia, yeah, Maria, Marie, Leon. So all of them indicate that they follow it and it looks fine. So if there are some problems, just report it right now. That's the time. So okay, I think everyone is fine. So let's continue.
So let's now start with the first worksheet. So click on item number 1, and this includes the first point here. This you should have done already, but I'm going to also be doing it now in the demo. But I will be using videos, so I will be fast forwarding this step, as downloading Fiji can take some time. So first, I'm going to open a web browser and go to the Fiji website, which is this one. And here you will need to select the appropriate version for your own operating system. I will be using the Windows 64-bit version because I'm using Windows 10 64-bit. If you are using Mac OS, please download our custom version, which we have mentioned in Slack and in the email. I will be now skipping forward to the downloaded zip file. I would encourage you to use a fresh, newly installed Fiji to avoid any conflicts with other plugins and to ensure that you have the most recent version. Okay, so I'm going to open this and extract Fiji from the archive on desktop, in my case, so that we can see everything. So I'm also going to fast forward the extraction. Okay, and now this Fiji is ready to use. So I'm going to launch Fiji by clicking on Imagej Win64. Your executable will have a different name depending on your operating system. Now, what we are going to do now is we are going to install the plugin that will allow us to connect to the remote HPC, that is the high performance cluster. So press help, not plugins, press help and update. Now this is a normal part of the operation of Fiji. It will be checking for updates. Please let it finish with checking the updates, and we're going to update it if there are any updates. So please wait. I will wait as well so that you can follow along. Okay, so now for those using Windows and Linux, you may have this window may have appeared, which lists the jar files which have updates available. So we're going to update. So please click the Apply Changes button, and it will Fiji will download and install the updates. Press OK, and now you have to restart Fiji to make sure that everything is running correctly using the new versions. Okay, so now we will be adding the update side of our plugin to Fiji so that we can download the plugin and install it here in this installation. So press help and then update. And it will check for updates, but now it should be up to date. Press OK. Now the Fiji is up to date. Press Manage Update Sites, and in this list, scroll down until you find the update site called P2E, IT for Innovations. So I'm going to show you which one. It's this one, and check the checkbox. And once you have checked the checkbox, press the close button. Okay, so press the close button, not the add update site. Just press the close button, and you will get this list of jar files which are to be installed. So press the apply changes, and now each of these jar files will be installed in Fiji. Press OK. Now we have to restart Fiji.
That restarting Fiji is a normal situation. If you update something, basically it's safe way how to be sure that up-to-date classes are really loaded. So it's normal.
Okay, now if you press plugins, macros, and then you should be able to see the last item, the last menu item, which is called the Parallel Macro Client, which is this one here. Do not click on it yet. We need to do the next step, which will be the configuration for the remote connection, which we will see in the next step. But for now, let's return to the worksheet. And if you scroll here down, you see this, there's this give feedback. And if you click on it, I would like you to fill out this form again for this section. And if you have successfully completed this section, press yes. If not, if you have encountered an issue, press no, and we will be helping you. And submit this form.
So I took a screen from you for a while. Okay, so let me recapitulate the what we call a grand scheme of things. When we were preparing this workshop, we had a certain expectation about what you have, what is your kind of routine, and what is your kind of probably the situation, and where you want to go after this workshop. So let me see how much in synchrony it is with what you are up to, and it will also explain the steps that we need to do in the things that will come. So we assume that, of course, you are working probably for some institute or for someone, and that most likely you have some image data that you want to process, probably a lot of data. And this data is most likely living on some file server within your institute, within the reach of in your local network, sort of. And we don't expect that you are processing this data directly on your laptop, that you not just download it and then you're crunching in there and uploading again. Instead, you probably most likely have some powerful workstation somewhere around, and you are sort of remote commanding it. Basically, this remote desktop session and VNC and TeamViewer and these kind of things. And you have probably like this connected from your laptop to the workstation, and on that workstation you run Fiji, we assume. And with that Fiji, that computer is of course hooked to this workstation, to this file server, and it's taking the image one by one and processing it. Because this is the kind of typical, as my experience is showing me, this is kind of the typical scheme that we basically, when we have a couple of images we want to process, we take one, we open it in Fiji, right? We usually start this macro recorder, and then we do something to the image. We somehow try to process it, manipulate. Eventually, we hopefully reach something that we are happy with. And then is the moment when on the macro recorder, there is this button that basically starts a macro editor, and that the content of the macro recorder is in that editor. And we probably wrap this code with something that loads an image. Then comes this processing of it, and then there's a piece of a code that we have to add that basically stores the image. And then this is like a beginning of our automation, right? We have this, and then we wrap it with the for cycle, and this way we kind of iteratively process images. So this is what we expect that is a routine for you, that you probably doing a lot, you know how to do especially, and you probably want to move a little bit beyond that in the hope that you have some high performance computing center around you, which essentially is nothing more than like a lot more of a powerful workstations hooked all together in a network that we need to reach it. We were expecting that it's not necessarily within your institute. If it is within your institute, then it's even better. But we are already, even for a case where, like we are facing now, when you are across the world, and this HPC center is in Ostrava, so we have to get to it. So that basically means we have to establish a connection. So that's exactly the first step that we will be doing. So far, we were installing a software on our laptop that allows us to do that. And we will now be looking in the steps how we can connect and get in touch with this remote center. And then the idea, I'm sure you already see it, we will have to upload the images, and then the images will arrive at these multiple computers there and will be computed at the same time with exactly the same script that I mean, of course, not only the data, but also the script has to be transferred. So that basically involves additional steps. So first of all, we have to connect to that. Then we have to upload the data. That is like an explicit step. Then we have to set up a job. We will explain that, what it is, and how we do that. A job is like a command to this high performance computing center that the data that we have just uploaded should be processed with the script that we've provided. So first step is connect, then upload, then start up a job. The job will be eventually executed on that center. And then last but not least, we want to download the data back because we want to see the result. So these essentially 4 steps are ahead of us. Now a little bit of reminder about this HPC computing center. Michal has already touched that. Right, these centers represent a huge computing power. Of course, this is the reason why they were built, and that's also why we love them and why we want to talk to them or connect to them. But as such, as being such a computing power, it is also a very expensive toy, and as such, it has there's a lot of restrictions and a lot of policies and rules and documents. Sorry, yeah, you know, it's from a computer scientist point of view. It's all the procedures makes a lot of sense. It's actually following our current knowledge and standards regarding security and stuff. But from a user point of view, it is just a lot of complications. You've already seen it, right? We couldn't send you a password in a normal email. We had to obfuscate it, and then the password was not enough. You actually had to log into some system, and there from that you had to download the key. And then, you know, the key, there was a lot of like, don't share with anyone. It's like the most precious thing. It's the key to your house, to the HPC. You must not borrow it to anyone else, and these kind of things. So this is what I have in mind now. So, but we've tried to minimize this effort for you, that you really have to somehow survive this to get the key. And once you have it, then you put it once and forever into this Fiji program. And hopefully from that moment on, you will be only taking care of the business of the setting up the scripts and sifting the data, and everything else is already kind of solved for you. Yeah. Since this is a precious thing, it's sort of a facility, right? We want to share it. I mean, the owners of the HPC Computing Center want to share it with others. That calls for a various rules and fair using policy in the first place. And that materializes in something that's called jobs, because job is the like a unit of command, how you can prepare a work that needs to be done on the performance computing center. And these jobs are planned, so there's a word like a term like scheduling and stuff, and we will also see it later today. It's not like not like connecting to a Windows computer and then double clicking an exe file and it just is immediately started. Unfortunately, it's not like that. So that's pretty much what we are up to now. So we will now look into a way how to connect to the center, and then we will be inspecting. We will be looking at the software what we have. We will show you how to start a job. We will explain what the job is and what are its parameters and so on. And then we will look into how to upload data, process the data, and how to get them back. So I'm sorry that I was a little bit intentionally very slow with that. I hope this was enough for Leonislas progress bar to get it, to make it to the end.
Okay, let's continue then to the next worksheet. So press next. And we're going to see now how to set up the paradigm for parallel macro. There are many ways to use the high performance computing cluster and parallelism in general. So there are many paradigms, and we're going to be using only one today. And I'm going to show you how to do this. And we can have profiles of these paradigms, and we're going to create one, and in order to connect to the high performance computing cluster. So let me show you, and you will understand. So now, as you can see, first on the desktop, I have placed my key file, the ID RSA, and then dash DD and so on, which is the username, the last part. So it's ID RSA and then the username. I have placed it on my desktop. You don't need to place it on your desktop, but I would like you to have this file ready because we're going to be using it in this section. So now please click on Open Fiji if you've closed it, and then click on Plugins. And then you need to scroll all the way down until you find Site Java Parallel, the menu item. And then you should see the Paradigm Profiles Manager. If you click Site Java Parallel, you should see Paradigm Profiles Manager. Click on it. And this window will appear. This, as you can see, has some horizontal sections. One of these is the new profile section, and there is this input field. Type in name for this profile. I'm going to call this cluster. So this profile is what we're going to be using to connect to the HPC cluster. And if you see, there are also columns. So the first column is name, and then the second column is paradigm type. As I've mentioned, we're going to be using just this paradigm type today, the HPC workflow job manager paradigm type. And this will allow us to use the remote cluster to connect to it. And in this horizontal section, we're also going to change the paradigm manager to the second option, which is the workflow paradigm over SSH, because we are going to be connecting over SSH. The other option would allow us to use a middleware, but we're not going to be using this at this time. We're going to be using the SSH one. So select the second option, which says over SSH, and not the hippie one, which is the middleware. And after you set this, press create. And at this point, there will be this SSH settings window. Here now, I would like you to scroll down in the worksheet, and you will find that there is an actual table under the image of this screen, of this window. There is, in this table, you can copy paste all of the details, but you will need to change specific values. So I would like you now to copy paste everything from that table to this form, and I will also fill this out, and I will mention which fields you will need to change with what values. So first item is the name of the supercomputer. Please copy and paste it. Do not type it in. And this name, notice that it is like a web page. It's salomon.it4i.cz. Please type it in exactly this way. And then the port number is by default 22, so you don't need to change that. The username, you will see that in the table, I have used my username that I'm going to be typing in here, but the last 2 digits in your username should be different. So please use your username here in this field that you have received in your email. So please use that one. Next, in the authentication method, just leave the default option of key file. And in the key file field, press the browse button and locate that IDRSA file that I mentioned. Here is mine. As you can see, it says ID_RSA dash and then my username. So I'm going to select that one. You need to select yours. And this is also at the end your username, so it should match the username in the username field. Now the key file password, as Michal mentioned, it is in the email, it was obfuscated. And in order to to make it correct, you need to change the capital letters with lowercase letters, and lowercase letters to capital letters, so to uppercase. So you need to switch the case of the characters. Okay, and type this deobfuscated password in the input field. And next we will see here in this section, the HPC settings section of this form. You will need to just copy and paste this the remote directory with Fiji. Just copy and paste it from the table. We will be using the same Fiji, and it is located in a shared directory in the remote the supercomputer. So it's in Ostrava, and we will be sharing this Fiji installation. And then you need to copy paste, just copy paste the remote Imagej command, Imagej Linux 64, just copy and paste it from the table. Now the working directory is a local directory. It is located in your computer. So you need to create now an empty directory. Make sure that it is empty, because our client, our plugin, will be creating new directories inside that directory. So please make sure it's empty. And you can create this anywhere on your local system, and then you can click the browse button. So I'm going to also create a directory in my documents, and I will call it WD for working directory. Okay, and I will select this by clicking browse, and then I will select the folder. And lastly, this is again a remote working directory. So this will also be located in the cluster, in the supercomputer in Ostrava. Copy and paste this value, but notice that it is using the username. So it lists the username as well. So as you can see, it has my username, which is 203601. Just replace that part of that text, only that part, with your username. And also small note that the remote directory with Fiji contains something similar to the username, but this is actually not the username. So please leave it as you see it in the table, and just copy and paste that from the table to the form. And once you're done filling this out, press OK. And now all the required settings should be stored for the connection to the supercomputer. So press select, and you will see that now in the selected profile input field, you will see that the name has appeared of our profile that we will be using. If that is the case, you may close this window, and we will not need it anymore, because these settings will be stored for future use. We could have created multiple profiles in order to connect to different supercomputers, but we will just be using this one today, so we'll not need this again. So at this point, please also, if you click plugins, scroll all the way up this time, macros, and then at the end, parallel macro client. If you click on it this time, if you typed in the settings correctly, you should see this window, this empty table. And if this is the case, then it works and you have successfully completed this section. So please scroll down in the worksheet and fill out the form. I'm going to fill it out as well. If it is not working, please click no, and this is the probably the hardest part of this workshop, as there are difficult. Now we can proceed to the next section, and here we will be submitting our first job. So we will be running our first parallel macro, and I will show you now how to do this. We will be using a pre-made macro that is parallelized, and you will find this in this worksheet. So, but let me show you, and please follow along. So now I'm going to reopen the plugins and macros and parallel macro client. I'm going to click on it, and now we should all see this window, and we can now right click and click on create a new job. This window will appear, and now we need to select the number of nodes. Please use 3 nodes, otherwise the example will not work. And we need to also select the input directory. So click on browse and create an empty directory. I'm going to call this directory hello, and then inside this directory create a new file, a new macro script, an empty macro script. I'm going to do this by creating an empty macro file, and an empty file, and then I'm going to rename it here in Windows. And I'm going to call this one hello.ijm. Make sure that the extension is IJM. This is the extension for macro. Now this part, if you have Windows, you can skip this part by creating the macro through the text editor in Fiji in the usual way. Otherwise, this part may be useful. So if you click on View in your File Explorer, and then Options, and click the Change Folders and search Options, and then click on View and scroll down. You need to remove the check mark from the option, which is called Hide extensions for known file types, and press Apply and OK. And this will reveal the extension of the file. So as you can see here, it was .txt, and I need to rename this to remove this so that it will be an IJM file. An easier way to do it, as I mentioned, is to create an empty macro using the text editor of Fiji and save it as an empty macro inside the empty directory. It is very important that you use an empty directory and not a directory which has other contents, because this directory will be the directory of our job, and anything along with the macro file that we will be using will be uploaded on the remote cluster as data for our macro script. So if there are other things in there, they're going to be uploaded, and it's going to take a while. So please create an empty directory, which I've called hello, and place your macro script inside and select it. Now I have selected the macro, as you can see, and the 3 compute nodes. In the number of nodes input field, I have set 3 nodes, and now I can press create, and you will see this new row will appear, which is our job. And you can right click on it and press the open in editor. In the Mac version, this option has been removed because there are some issues. So please, in the case of a Mac, open the blank macro in your editor, text editor of choice. It can be any text editor. And now you need to search or scroll down in the worksheet until you find this link here called this example. So since you do not have a macro that is parallelized, we provide you with this this example here. So click on this, and you will see in this page this user.ijm. Click on it, scroll, and you will see on the top left there is this raw button, which when we click on it, we will receive just the plain text of this script, and we can copy it by dragging this text and right click copy. In Windows, you can press Ctrl A to select everything and copy afterwards. So copy and paste these contents in the text editor and save. So file save in the text editor of Fiji, and then close. And now we need to upload the macro file. So right click on the job and click upload data. Any file that is in the directory along with the macro file that we selected will be uploaded as data. So that is why this is named upload data. And once you see in the upload column of the table that it is done, you will see first the timer and then you will see that it is done. Then right click on that row again and press start job. Now you will notice that the status column has changed, and it says that the job is queued. So it's the job, since we are sharing the supercomputer with multiple users, the job will be placed in a queue and wait for the resources to become available in order to be executed, to start running. And you see that the creation time has been filled in because the job has been placed in the queue. So the creation time is the time when the job is placed in the queue. The start time is the time when the job begins running, and the end time is the time that the job has finished the execution, either by being cancelled or finished or otherwise has stopped. And as you can see now, the status changed to running. So now this job is being executed remotely. I will skip this step because we will see it in the next section. But you see that it is running. This is running in the supercomputer in Ostrava, and not locally on your computer. You can see the start time has also been filled out because the job is running, and now my job has finished. And you see that the end time has also been filled in here. And I'm going to right click on the job. So when your job has finished, you can also do this step, but I'm going to show you now. So right click on the job once it has finished and click the download result. This will start downloading. and you will see this timer. Now this will take longer than uploading because we are also downloading the resulting images. This demo simple script that we are using does not have any input, but it generates 3 images. It actually generates one image for each compute node that it is running on. So each computer that it is running on. The cluster is made up of multiple computers, and we specified 3, so we should get 3 images in our results. So the results have been downloaded, and once they have been downloaded, we will see they are done. And now we can right click and click on the Open Job subdirectory. And here we will see the downloaded results as well as some settings. This directory, the working directory, is contains the configuration, the settings file for this job. And unless the user changes the default option, then the output directory is the same as the working directory, and the output will be placed in this directory as well. In this script, we have placed the output in a different directory called output, but this is just in our script. The output is usually placed in this folder, and if you notice in the path of this in this directory, you will see that it is using the working directory as specified in the previous configuration step, and then it generates this directory. In my case, it is 3 because it's the ID of the job. Yours should be 1 unless you have run other jobs previously. It should say 1. And in the local directory we created in the previous step during configuration, you will see all of the local files of the job. So if I double click on this folder now, and I will show you this generated image, it's just random lines and hello world overlays, so text overlays that have been flattened on top of this image. And this is just to make this script that will take some time to run, and you can see the result. So now we can return back to the worksheet, and if you have successfully downloaded the results, then you can consider that you have successfully completed this step. Otherwise, please select no, and we will help you with this with any issues that may have arisen. Okay, so Michal, do we have answers? Okay, so let's proceed to the next section. This is about how to inspect progress in your job that we executed, and see the output and the error output that you would normally see on your screen if you run the macros locally. But now, since we are running the scripts remotely, you need to see this in this plugin. And now I'm going to reopen the Parallel macro client from macros, plugins macros, and if I double click the job that we just ran, the row of that job, Then we see these tabs. The first one has progress by task, and each column is a node, compute node, and each row is a task. The error output is here, where you will see the error. The other output is what you see with print statements on your screen normally if the macro was running locally. Job subdirectories are just the directories we use, the input, output, and working directory. And the data upload is just a list of the data we uploaded. There are two files here, the hello.ijm, which is our macro, and the parallel macro wrapped script, which wraps our script. So it adds, it appends to that script the parallelization functions and the progress reporting functions we're going to see next. This is done because it is much easier than using the macro scripts call function, which calls the Java implementation of our parallelization functions, which we are now wrapping and hiding inside much easier to use macro functions. So that is why this script will always be generated on upload, and it is our script, the script that you create, the user script, with these easy functions appended. So this was a very short section, but this is where you will find the output that would normally be on the screen, along with the progress that you will see how we make these gauges, these progress bars appear in next in following sections. So please also give feedback here. I will give feedback as well. So if you run this the previous job successfully, then most likely this is working. And there may be some errors because in the other output tab, because we are using the same shared Fiji, and there might be some file lock related errors. There is a fix for that, but usually we would each have an installation of the remote Fiji in our home folder, so this would not be an issue there. So Michal, is everyone okay?
All right.
Yeah, thanks. So I apparently forgot to do it before that. Sorry for that. But now let's kind of get back on track. The HPC center, it's a lot of computers, but we call them nodes. That's the terminology. So you probably saw it in a dialogue that he was asking how many nodes. So that refers to how many computers. Now, we also already know that the job is the scheduling unit. This is basically the definition of a task that needs to be there. It consists of a pieces. These are, you have to say for a job, how many nodes you want to occupy, how many computers you want to use. You need to say for how long you are going to use them, which at the moment is kind of hard coded, unfortunately, in our script, and we will change it. So you need to say how many nodes for how long. There is a queue. There was also this term there in the job. The queue is essentially the enforcer of a certain policy. So for instance, the queue can restrict you. There can be queue that would be running jobs only on the computers that are enabled with GPU cards. Or there can be queue that says within this queue, jobs cannot run for longer than 2 hours. Or there can be queue, which is like a kind of for quick short jobs and prioritize that these jobs are kind of scheduled as soon as possible. You can imagine, right? This is basically something that comes from the HPC center. They define what sort of queues they will offer, and they have to tell you which are those that are available for you, and you need to specify it here. And last but not least, the important thing is the script. You have to tell what is actually the script that needs to be executed, right? So we had it there as well. When we create a job and submit it there, let's suppose that the job has been scheduled, that the job is currently running on the HPC node, which is here illustrated that some of these computers have this Fiji logo. So it's we are in this case using 11 jobs, 11 nodes. The macro, the one that we submitted through our HPC workflow manager, this one macro, exactly the code as it is, it's multiplied, it's copied, and it's running at all these computers independently. So all these computers are executing exactly the same macro, exactly the same piece of code. And now you may be wondering, okay, what now if we are running, if all the computers are running the same code, how does the macro decide which portion of the data it needs to process? Because if this macro cannot tell a difference, if it would be executing the same data, then what would happen is that we will be executing all this everywhere the same data in parallel but repeatedly, right? So that's what we don't want. For that reason, we have when you enabled our plugin side, our plugin in the Fiji update side, this plugin also brings in a bit of more functions into this macro language. So one of the function is called target size. That function returns how many nodes are allocated currently. This number or the return value of this function is a constant value. It returns it on all the instances everywhere the same. So yeah, another function is target rank. This is the crucial function. This function gives back a sort of a node ID, and as such, it varies between nodes. So let me illustrate it graphically. Here we have altogether 11 nodes allocated. So this target size on every instance, on every macro running on every computer will always return 11 in this very case. But this target rank will on this computer, for instance, will return a value of 0. On the next on this computer, on this node, it will return a number of 2 or a value of 2. And basically this tells you like how many kind of computing units you have at hand. And this target rank basically tells you kind of like which portion of the computing power is represented by this node, and you can use this information, and we will show you how to do that later. You can use this information to kind of cherry pick the relevant portion of the data, and this way you basically split the data into multiple chunks, and this way you assure that you are processing always a different part of your data. So that's the main trick to it, and we will now proceed with programming, and we will try to demonstrate to you the use case of the getRank function and so on. Stefanos, please.
Is this clear? Is this clear? Do people want to maybe ask a question? Because that's fundamentally what this is all about, actually. Okay, then it's clear. Good.
Stefanos, please can you continue? You are muted.
Okay, let's see these functions that Vladimir mentioned. We have so we have proceeded to the next worksheet, and I will be typing this step by step. But in order to save time, you can just use the last version, the last snippet of the code when we are creating the new macro file. So let me start the demo, and you will understand. So I'm going to open the plugin again. So plugins, macros, and parallel macro client. And we will be creating a new job. So right click new job. And we will once again, we will need an empty directory. Please create an empty directory, a new empty directory. I'm going to create it on the desktop, and I'm going to call this one simple, because this is the first simple macro that we are parallelizing, and we will need the IJM and IJM file here inside the empty simple directory. So I'm going to create a blank macro script, and I will call it simple IJM as well. You can use any name, but I will use this one and select it. We will need to use 3 nodes for this example as well, and please use 3, otherwise it will not work. Press create, and now we can upload. We should always upload. No, we don't. Before we upload, we need to edit. We need to edit this. If you are using Mac, please use the editor from the Fiji menu and create it like before. If not, just right click on the new job. So click on that row, the new row that was created, and now select the opening editor and paste in the last snippet of code. In your case, I'm going to do it step by step, so I will paste in the first snippet. This is the serial version of the program, so this will run sequentially, like in your local machine, like it would run on a local machine. And this is just 3 print statements. This is this has a title, and which is the greeting program, and there are 2 more lines, and which is hello and bye. So the compute node is a computer in the cluster. So we will be using 3 computers, and we want each of these 3 computers to say hello and say bye. And we also want the title to be printed once, as it is currently. If we run it on the cluster, these 3 lines will be printed 3 times, and they will be identical, so this will be wrong. So in order to make this truly parallel and do what we want, we need to add these 2 function calls. The first one is the par init. All of our function calls, all of our functions in Parallel macro begin with par, so that once you begin to type them in the text editor of Fiji, you will get auto-completion. And so if you type par, you will see all of the available functions. Now, when we end the script, we need to type in par finalize. These 2 will initialize and finalize internal variables that are used by Parallel macro, and we need to add these 2 functions in every parallel parallelized script, parallelized macro script that we are creating. We are using OpenMPI in the underlying implementation, and this is the exact equivalent with the initialization and finalization there, but it's not important. The important is that you need to always use these 2 functions when you are parallelizing a script, par init and par finalize, and the init needs to be in the beginning and the finalize needs to be at the end always. So now I'm going to be proceeding to add the check to make sure that the first line, our title, which is the title of the program, the greeting program, that this will be printed only once. So in order to do this, I'm adding this surrounding this print statement, and any other code, if you wanted to execute any other code only in a specific node, we would do the same. I'm surrounding this with an if statement, and inside this if statement, I'm checking the ID of the computer, the ID of the compute node. Each compute node has an ID always, and these start from 0, 1, 2, and so on. So in order to get this ID, we call this function the par get rank. So this is the third important function for parallelization in the parallel macro, the par get rank. which and we store this rank in the variable myRank. And if we were to execute this, only the first node, only the first computer with the node with the ID, with the rank 0, would execute this, would print this, the title. So the title is only printed by the first computer, and we will see it only once in the output. I'm also going to replace the last two print statements to print the ID of the node that is running that code. So in this case, all of the computers, all of the nodes will run these two lines. So we expect to see, since we are using 3 computers, we are expecting to see the messages, hello, I am node number 0, hello, I am node number 1, and hello, I'm node number 2, and the similarly for the by messages. Now this line I added in line number 3, the fourth parallelization function we are introducing is the par get size. The size is the total number of computers, the total number of compute nodes you are using in the supercomputer, which in our case is 3. And I'm going to print this information in the print of line number 5, so in our title. And I have made an intentional mistake here. Do not make this mistake. I'm making this mistake to show you how to debug our macros in case you have made mistake. Now I'm also going to add this, the last parallelization function that we will be seeing today, for which is the power barrier. And the power barrier will make sure that all of the computers we are using we have reached this point in the code, have reached line number 8 before proceeding to any lines after that, after line 8. So line 9 will be run after every computer has executed everything until line number 8. Why is that necessary? Because the computers are executing the code in parallel. It's not guaranteed that they are executing the code at the same time. So one computer may have executed the code until line number 7, while another one may have finished, and another one still may be at line number 3. So in order for us to print the hello statements, the hello, I am node number, and so on, before the by from node number and 0, 1, and so on, we need this barrier. So this way we guarantee that every hello will be before every by message. Okay, and now we'll save this. As you can see, there is this auto-completion in case you, in the future, you're using parallel macro and you forget which functions are available. You can always use the auto-completion to remember, and there's also help. And please save the script by file save or Control-S and close the window. Right-click on the job, click on upload data. Remember to always click on the upload data. If you have changed the file, only the changes will be uploaded, but you need to press that. You need to click that menu item. Otherwise, if you start the job and you haven't uploaded anything, the job will be in queue, will be in the queue, will be queued, and you will just get a warning that you did not specify any files, but your job will have spent the time to receive the resources to be in the queue, and you have wasted your time. So now we have uploaded, so we can start the job. So you should start the job as well. and this will run. But I have intentionally made that error. So in my case, I will forward this a bit, and we will see that now it's running. Okay, so the status is now running. And once it has finished, I'm going to double click on this job once it has finished to see the output, and I can immediately notice that the output, which would regularly be in the monitor, if we run this in serial in regular Fiji, is wrong. So I can open this in the editor again, and we would see the mistake. And if you did not notice the mistake, you can click on the error output tab, and here you will see the error messages that would normally be on the screen. And there I noticed the syntax error. So this is the missing quotation at the end here of the nodes, and I will fill this in. And now this is correct. So I will save again and repeat the steps. You don't need to do this. Just showcasing how to solve a bug, and this is also an opportunity to show you that now that I have re-uploaded and I can restart the job, and I can then close the window. And since this job is executed remotely, the status will change to running and so on, even if I'm not using Fiji, even if I close every window of Fiji. Since I have set the job to start and run, I can, it will be scheduled and executed in the remote cluster in Strava. So now we see that it is running. I could have, so we could have closed the program, do something else, do some other work, and the job would have run and finished. So whenever there is we have time, we can go back and look. So you don't need to have this program open while the job is running. And you can and now if I double click, once again we can see the output in the other output. At this time we notice that it is correct. And let's see if we did this correctly. So the title of the program, the greeting program, appears only one time, and it correctly says that we run it with 3 computers, 3 compute nodes. We also see that every hello is before the by statements. And I would like also that you notice that although the buys are after the hello messages, which is the result of the par barrier that we added, the par barrier function that we added. The rest of the messages are mixed up. So since we are counting from 0, the third computer ran first, the second computer ran second, and the first computer ran third. So you see that they are mixed. And in fact, when after the barrier, in the by messages, the third computer ran first, the first computer ran second, and then the second computer ran third. So the ordering cannot be guaranteed between the different computers, but we can have a synchronization, have a barrier, which will guarantee that every computer has reached the point before continuing to the next. But we want to keep this minimum because these add extra cost. But This is everything for this this part, for this section, and I will go back to the worksheet and fill out the form. Please respond, and we will solve every issue. Yes. So let's proceed to the next section. Oh, sorry. So this is the next section, how to use the progress reporting functions. These are just for reporting progress, and we will be seeing how to do this. So this progress will be reported in that macro progress tab in the dashboard. So let's create a new folder and call this one progress, and we will be writing this script in order to demonstrate how to do this. Once again, you can use the final snippet in order to save time, but please see, I will do it step by step. So I'm going to call this progress.ijm. And then I will just reopen the Parallel macro client. And I will be creating a new job. In this example, you should use only one number of nodes. I'm going to be using 3, but you should use only one. There is no need to use more than one, because we are just demonstrating how to add the progress reporting functions to create the progress, the progress bar. So select the macro file, the empty macro file in the empty directory. Use only one number of nodes, not 3. I'm just using 3, but just use one. And now I'm going to right click and open the editor. So open the editor, and I will start with this 3 fake image operations. So in order to make sure that they will take some time, I'm going to be using these functions. This we suppose that they are image operations, and I will use the wait function to wait 5 seconds for each one of these. And I will change the image operation name to 1, 2, 3. This could be any image operations that you like, maybe blurring or some other operation, but I'm going to using this example to make sure that we have a more deterministic example, so that we can understand the output. And let's imagine that we want to apply this into 120 images. So I'm going to add a for loop here to repeat these operations. And we can imagine that there are 120 images, and we are applying 3 different image operations on these images. But and as you can imagine, this is 120 images multiplied by 5 seconds. And there are 3 image operations that take 5 seconds. So if you do the calculations, it would be 30 minutes. And as you saw earlier, there is this status, the status column, but that will just inform us that the job has been either in the queue, or it's running, but it will not give us any any idea as to the actual progress. So for half an hour, it will just say it's running. So we will add here some code to show those progress bars now. So as always, when we're using the parallel macro functions, we need to add the par init at the beginning and the par finalize at the end of the script. And now we need to define the tasks. So we will be reporting the progress by tasks, and we need to specify a task description for each one of these tasks. So we're going to have three tasks, one for each image operation. And since these are not real, I just named them first op, second op, and third op. These are the descriptions that will also appear in the macro progress tab in the dashboard. So these are the exact names, the exact text that will appear there. And we need to call the par report tasks, not progress, as I have written here. So I'm going to correct this. If you have forgotten or did not remember which one to use, remember that there is auto completion, and if you start typing the par, these progress reporting functions are also available there, and you will see also the help that is available. And this is finalizing the task descriptions. So after the par report tasks function, we cannot add any more tasks, but we can now start using this par report progress, which is the third and final function for progress reporting that we're going to see today. And this one will take the task ID and the percentage of the completion of that task. So here we are going through the loop, and we want to increment the progress by 1 each time we perform one image operation to the images. But it can be difficult to remember the IDs because some tasks may not exist for some compute nodes. If like in the previous example, we want to run something only once, so we should and I suggest that you always do this. You should use a variable to store the ID that is returned by the par add task function. This way, we do not need to remember the IDs at all. And now, finally, we need to add, because of macro, that in it every numeric variable is of the double type, so they're not integers. It's and the division can lead to there can be errors, so may not get to exactly 100%, and we want it to, when it's finished, to say 100% so that it will be done. We add these three par report progress with 100% at the end to make sure that it will say it's done. So now it's ready, and save this macro file. You should use the last snippet. Remember to upload. Okay, once it has been uploaded, then start the job. And remember that this job is when it starts running, like it is in this demo, it will take 30 minutes. So we're going to see how the progress bars look like now. Going to open this. Okay, and as you can see that it might take a while to load, but you will see these progress bars, which are incrementing every 5 seconds. So the first hop will now become 4%. And in 5 seconds, the second hop will become 4% as well. And then in another 5 seconds, the third hop will become 4%. And then we start from the beginning. I will speed this up. So once you have seen this and it is working, unless there is an issue like we saw in the previous section, you can close this window once you see that this is working. You can close this window, okay? And since this will take half an hour, we can right click and click the cancel menu item. So just when you've seen this effect, close the window and right click on that specific job and cancel this job. I'd also like to mention that you can have multiple jobs queued or running at the same time. So you need to select the specific one when canceling, or if you select a different one, that one will be canceled. When you're canceling, and as you can see, it might take a while for it to display as finished, but it will be canceled. Take some time for the scheduler to cancel the job. And once you see it, cancel the job and go to the bottom of this form and submit the feedback.
Yeah, so this is my last intermezzo today. Before we move to another section where we will be looking at the real application and how an example, how it could have been parallelized, I would like to present you this sort of a cookbook. And it's essentially a bit of an abstract thing because, well, you will see. So suppose you have a certain volume of work that needs to be done, which is graphically represented with this purple rectangle, right? The work needs to materialize in anything that Imagej can do. As something that can be, for instance, macro recordable. And the volume ideally needs to be, we need to figure out a way how to split it into tasks, because otherwise it's like if you want to eat a giant pizza, if you have just one bulk pizza, then it's only one hand that can grab it, and so only one kind of person that can eat it, right? If you manage to tile it into multiple pieces, then more people can grab their own piece and work on that or eat that, right? So this is the idea, and this is again something that cannot be really automated. It comes with your problem, with your task. You have to figure out how to split your task into smaller ones, and what you also have to provide what you want to with them, which is termed here as the work. So in now this is easier said than done, right? We have to realize that we are working with the computer programs. This macro language is essentially a programming language, and in programming we have to be a little bit organized. So we have to come up essentially with this sort of a mapping. We have to figure out how to refer to individual tasks, and to refer means that we can, for instance, number them. So in this example, let's have a 42 tiles, 42 subtasks. It can be 42 images in a folder. It can be 21 images, each of 2 channels. It can be 42 Z slices of one 3-dimensional image, right? You probably already get the idea how you can split your task, your volume. Ideally, a processing of a certain task must be independent of any other task. So that, for instance, means that you can process them in any order. Always try to answer this question. If I can process my tasks in an order, then it's fine, and then you can throw it on the HPC quite easily because there are no interdata dependencies. Now, it's also good when you have your work as materialized already in the form of a macro script. It's always good to kind of wrap it into a function, and that function should ideally get just one parameter, and that's basically the reference on the task, on the subtask that this function should be processing, right? And most likely you will probably also end up having a function for loading and storing loading the data of the task, processing it, and storing, right? That I'm sure you recognize this pattern. This is the, I would say, our everyday bread, right? We typically, I already said it, we typically open one image, do something where they do process it somehow, we get some result, and then we want to save it. That could, in programming, could take this form, loaded image and so on. And then comes this automation, right? We take image one by one, for instance, from our folder through this load function, we take them from this our folder and we process them. I'm sure you are very well familiar with this. And now let me show you how you can parallelize that. There's essentially a general rule. So let me first massage this, this term. So this main for cycle, here's a, you probably knew that there is an alternative way of writing this increment like this. Now, suppose we have this code, we have it in one computer. This computer is represented with this kind of shade behind that, right? So it runs one script, one instance in the memory of one computer. And what it does, obviously, it takes the tile one by one, and eventually it processes all these 10 tiles, right? This is the volume original that we want to process, and this is only showing that what everything we process. Now we can upload this macro on the HPC system, and then we already saw it. One macro is executed, the very same code is executed at all the computers. So here, let's take the example of 3 computers. So we have these 3 scripts running on the 3 computers at the same time. If we let it go like this, then we would have a parallel execution, which is nice. But on the other hand, it's very ineffective because the code is still the original one, and that goes over all these 10 tiles. And of course, if we now look what's been covered, what's been touched, we see that we've processed every tile 3 times. That's kind of not nice. So what we can do about that? One thing, remember we had this target size function. So we can use it and basically let these programs operate and jump over our data in these steps. So that graphically looks like this. Parallel execution, every third tile is touched, right? The coverage then would like this. That is, I mean, at least one thing is good that we managed to end up earlier because fewer tiles, but still it's not the really what we wanted. So we're let me also only change here, introduce here this space. It's just so we could easier see the next step, so not to get confused. Now we utilize this target rank, this function, and that's we are finally arriving to the final solution. So we have here again the same code on 3 places, on 3 computers, executed, and because of this magic of this target rank, we're still jumping over the tiles, but always every computer starts at a different kind of offset, and it finally does what we wanted it to do. So we touched every tile, we have processed all what we needed, and everything was done only once. No tile has been accessed twice, no tile was left behind. So it's pretty much simple like that. If word is ideal. Let me summarize that. So we have this kind of known serial pattern. We want to parallelize that, so that is easy. Basically, it boils down to replacing this for cycle with a sort of smarter one. And we also have to add this decoration to initialize and also then close the parallelization, right? And this is basically all to it, except that as we've seen, this creates a macro that runs in parallel but doesn't report back. Here, this is just a homework. You can reach this PDF on the Slack. You can inspect this. It's only an example that the mapping of your problem into this kind of addressing scheme can get arbitrarily complicated. We will see in the real example that it will get even a little bit worse. We would actually need to have an extra helping functions to figure out how to address the individual tiles, how to cherry pick the relevant portions of the data. And it really depends. Here the example is showing like 21 images with 2 channels, but I will leave it as a homework. I'm sorry for now. For now, let's focus how we can extend this already parallel code into a code that's decorated with progress bars. So on the left is the original parallel code. On the right is the same code at the moment. It's only a little bit more stretched because we will be adding code here and there. We have to start by defining the progress bars. So the macro, again, one macro, one code, executed in many computers. It goes from top to bottom, right, sequentially, right, as usually. So it first finds this, first it hits this for cycle. Notice it is the same cycle as is down here. So it basically what it does is that this I will go over the same sequence of numbers. And for every such I, it would create an own progress bar with this function. Now, once this for cycle is over, then this code is running on a node on a HPC in the HPC center. We need to tell back to our laptop, to our client, to our Fiji, that what progress bars, what gauges will be displayed. So with this function, we basically the defined progress bars, we kind of transfer them back. Now the running of the code continues. There is some function, okay, function. Let's just skip it until we need it. And then the code crunching continues, right? We get to this for cycle again. Here, actually, the actual work is done and it's calling back this function. And now this function is processing one particular task that we want to take care of. And we are seeing here these three kind of items like loading and processing and storing. And we just decided let's report after every this stage is done. So first of all, there's a bit of technicality. These eyes are actually iterating over, in the domain of our problem. We have somehow figured out how to map the program into numbers. But this, when we want to update these progress bars, we are also referring to them with the number, but the sequence of number is different here. So we basically need to translate from the sequence of eyes into the sequence with which the progress bars are represented. And the sequence with the progress bars is easy. The first edit progress bar is referred to with 0. Next edit progress bar is referred with 1, and so on. Right. So with this formula, we basically bring us from this I to the appropriate progress bar that was created here. And now when we have the reference on it, we report the progress. Easy like this. We tell to the appropriate progress bar to set the progress to 20% because we just decided that load is worth of 20% of the entire job, right? And then we just decided that, okay, finishing processing of that image could be worth of 80%. And then of course, when we are over then 100%. And that's all to it. So basically then this reporting can give you back this, for example, this kind of view. And that's essentially the take home slide. So we started with this original serial, good old pattern where we were processing sequentially certain images or certain data with this function. And then we managed to get it, to have it in parallel and decorate it with progress bars. It is a bit of an effort, but I think it rewards in the long term at least. I have also here is one little technical glitch that if you were to try it now or in the coming days, we've noticed that on some platforms, these functions, target size or target rank, doesn't written back integer but string, and the string is kind of not cool for this math here. It's computer doesn't know how to increment I by some string, so it's good to have this for liner somewhere around that basically with this parse int brings you from these strings into integers so that this all could work. But please, as I'm trying to show here, oops, it's a temporary thing. This is what we suggest to imprint in the memory. This is a temporary glitch. We will fix it soon. And that's all I wanted to say. Thank you for your attention. And I would like to ask Stefanos if he can guide us through the real world example, how a task can be parallelized.
Okay, so let's see the real world example. I'm going to switch to the demo first, and I would like you to follow along with the demo. In the first part, we will be setting these two jobs to run this time. The first one, we will be using the first snippet of code, which is the serial code, the original code that's running, that could be running on the local machine, but we're also going to run this on the same cluster so that we can have a comparable time, because the machines are different. If you run it on your local machine, it's a different machine than those computers that exist in the cluster, and we want to compare the time between that serial code and this parallel code, which is the second snippet. So I'm going to show you now in the demo how to create these two jobs and start running this. And we're going to leave them to run and see what's the time, and so that we can compare. And then I'm going to explain what we did to parallelize this. So let's see. So once again, let's go to plugins and macros and parallel macro client. And now let's create the first directory, which I'm going to call Bruno Serial. Bruno is a real biologist, and he has provided this script. He's called Bruno Valentini, and I'm going to call the empty file inside the empty directory Bruno serial.ijm. And in this file, we're going to paste the serial code, so the first snippet. And right click and create a new job. Select the empty directory we just created, the Bruno serial. Okay, and then the macro file. Just leave one node. This is the serial version. We're going to run it using only one computer. This now right click, open the text editor and paste the serial code. If you are using the Windows and Linux versions, otherwise use your preferred text editor. And just copy and paste it. So this code I'm going to explain shortly. But first, you need to change this line number 3 in the serial code, the first snippet. Change this line here, the contents of this variable with your username. So mine is, as you can see, with the 01. Just replace this last part with your username. This is because while the input, we will be using the same input from a shared directory, but the output we will be saving in our own home directories on that remote cluster in Ostrava. So we need to specify the username for that path. Please replace this line number 3, the value with your username, and then save. Click upload the data. So it's going to upload the macro, and then right click and start the job. And now it will be queued, and sometime later it's going to start running. But let's also start the second one. So let's create an empty directory. I'm going to call this Bruno Parallel because this is the parallel version. And I'm going to create the empty macro file, and I will call it Bruno Parallel.ijm. And I'm going to create a new job, specify the blank macro file in that directory, in the Bruno Parallel directory just created. So this one. And we're going to be using 4 nodes, which is the maximum for our tutorial, for our workshop, and press create. This is an artificial limitation so that we all get the chance to run this.
Actually, but can be more, because there are people missing here, but use the correct queue, the one starting with R.
And the maximum is
Yeah, so there are only half attendance, so it could be up to 8 nodes, I think, if you don't have any limitation in the script.
Okay, so no, there's no. So use 8 nodes. If you haven't submitted this already, use 8 nodes for the parallel, the Bruno parallel job, and specify the queue in the queue instead of the QX value. Specify that R number that Pavel has posted in the Zoom messages, so that it will not have this limitation, and you can use 8 nodes. Ideally, we would be using 9 nodes for this, and you will see why when I explain the script. And once you have created this job, just upload. But first, before you upload, before you upload, paste the parallel code, so the second snippet, and we need to locate, after you paste this in the editor, we need to locate that username. This time it is in line 40, because we've added some procedures which I'm going to explain. And in this line 40, please change my username to your username. So because it's going to be used later in line 50 for the output folder. After you have saved you have modified, saved the progress file, then upload the data so that the macro is uploaded, and then start the job. And once you've done that, just leave this job to be queued and run. And I'm going to change back the worksheet, and we'll show you the results later. But now I will explain to you what we are actually doing in this real world example. So this script is converting this CZI files. There is a single CZI file in this case, which is 1.9 gigabytes. It's large. This file, this is a I file. We want to convert to TIFF, this format file, but we want to actually split the different views. So the CZI file is a microscopy file from a microscope, and it contains 9 views, and we want to take these 9 views from the CZI file and save them as separate 9 separate TIFF files, TIFF files, and also some movie files of the type of AVI file. And if we were to look at this in the flowchart, it would look something like this. So the original script would look like this. It would first read in the file. So there is a for loop. There's a for loop for the views. So we have a single CZI file in this example, and it has 9 views. So for each of these 9 views, it would perform some pre-processing operations, a rotation of those views. Of for each view, the view would be pre-processed, rotated, enhanced in some way, and then some maximum projection, which takes more time. It would be calculated, and then for the next view, and so on for 9 views. So this would happen 9 times in a series. So 9 times this duration. So because I have already run this, I can tell you that each of these views take 1 minute to be calculated. It's not particularly slow, but there's a time limitation for this tutorial. So it takes 1 minute for each one. So in all, it will be 9 minutes to execute this this script serially. But if we were to use the ideal of 9 nodes, it would be converted to this, which for each view would be calculated. The operations would be calculated in parallel for each view. So you see there is no longer a loop here. This triangle and this circle has been removed. They just executed in parallel in different computers, 9 computers ideally, and it would run in 1 minute instead of 9 minutes. In our case, we're using 8 nodes. So unfortunately, one computer, one node, will be processing 2 views. So it will take, because the rest of the nodes will have to wait for the slowest, it will have to take 2 minutes, because we will have to have the time that it takes for 2 views to be processed, so 2 minutes. But starting from 9 minutes, and if we had more SysZI files, so a list of many 1.9 gigabytes SysZI files, as you can imagine, this time would add up, and it could be measured in hours or even days if we had hundreds or thousands of them. And now I would like to show you the parallel code, and I will simply highlight only and explain the parts that we needed for the parallelization. You will see that you will recognize many of them from the previous 2 examples, and there are some additions for splitting the work. So splitting essentially the loop, splitting the views into groups, so that each compute node will execute its part of the operations required for a view. So we're splitting the views into groups so that each computer will execute its own set of operations for those views. So the first addition is this function, which calculates the number of views that will be processed by a computer. So this will take as input the size, which is the total number of computers we're using, and the total number of views, and it will return the number of views that that one computer will perform. So in our case, it will return, if you're using the 8 nodes, it will return 1 for all but 1 computer, where it will return 2, because there is 1 view that remains and needs to be executed by the same computer that is already executing 1 of those. The second addition is this function, which calculates the start and the end of the interval. So it will say that it will start from 0 to 1 so in our case, with the 8 nodes, it will be, for the first computer, it will be 0, then 1 and 2 and so on, and the last one will have 2, the interval which has a length of 2. And then you recognize this as we always add the power init. This you will recognize from the previous example. It's to add the descriptions of the tasks and finalize them. This you will recognize from the first example of the simple parallel macro, where we are getting the rank, the ID of the computer, that is the ID of the computer, and the size, that is the total number of computers. Then these are the same as in the serial code. Everything is the same until this part, where we are essentially just calling the first 2 functions that I've explained that we added. And we have some diagnostic messages so that it will print if you look at the output, once this has been executed, it will print the interval and the size of the number of the views that its node calculated. So in our case, it should say rank 0, size 1, start 0, end 0, something like this. And then here is the for loop that iterates through the views. And here, instead of 0 and instead of 9, we have the interval of its, the start and the end of the interval of its computer. So this is where the actual splitting is done. And this code inside the loop is essentially the same, but there is this added report progress calls, which we are using to show the progress, which you also saw in that example. It's the exact same as there. So these are the same with the addition of report progress, the same as the serial program. And here I've added these 3 lines. First one is diagnostic, to print the time, and this is to showcase the time before synchronization. So some you will see in the output, and I will show you in the output that some computers will have finished earlier since they are running just one view, they're calculating just one view, while after the barrier we're getting the time that all of them, the slowest one of them took to finish, that is the whole work was executed in this time. So the total execution time, the slowest computer then took this amount, and that's why I'm using the barrier to get that time, that the final time. Then the power finalize, which is used everywhere for the finalization. And if you want to parallelize your own macros, I would take these 2 snippets and compare them and replace my work, my operations here, and with minor modifications, it would work. Or you can use these functions and apply them, add them in your existing macro appropriately, but you need to find a way. And if you have a for loop with files, as mentioned, then I would strongly suggest just using the same way of splitting that workload, and copy and pasting these functions, reusing these functions to split that work. So thank you. That's for this part of the workshop. And please fill out the feedback. And I'm also going to show you the results, although you're going to also see them later. So I'm going to fast forward a bit here. We can see that the time is indeed the start time and the end time in the first job is indeed 9 minutes. And if we double click the second job, we will see that the output in the other output tab, which these are just the camera warnings. And we will see that the time its view took around 50 to 60 seconds, so around a minute. And finally, the total execution time took 167 seconds. That is for the 4 nodes that I ran this with. You're running with 8 nodes. So it's the total execution time should be 100 and something more than 120 seconds, but around that mark because it's 2 views which take 60 seconds each, so it should be 120 seconds, so 2 minutes, from 9 minutes to 2 minutes. And if we were using the ideal of 9 nodes, it would be 1 minute. So thank you. And
hello, I'm Daniel, and let me introduce you OpenMPI enabled Fiji with SciJava Parallel Mpi, the another way how to parallelize your scripts on a cluster. So in previous code examples, we had to instrument our scripts with some MPI-related functions. We had to deal with ranks, chunks, synchronizations, barriers, and more MPI-related concepts. We also had to split the problem into the chunks and let some nodes to process them. This can be a challenging problem, especially for biologists without computer science background. It can be also hard to develop it on the first try, and it takes time to develop these solutions. So we have developed Imagej Plugin, which makes it easier for the end user, so he does not need to handle any MPI-related terms. Our plugin overrides some Imagej operators with MPI support. For example, addition, convolution, which is pretty common in image processing, projection, and for example, edge detection. So biologists can use their scripts as they used to. They don't need to do any modifications from their side. They just need to install our plugin on the cluster and run their script. This plugin will be soon available through PG update sites, so it will be even more easier to install. So how it looks for the end user? At first, this example shows easy example how to make image board. In these 2 lines, we create a kernel, Gaussian kernel for the blur. In this line, we load the data set from the disk into the memory. Then we prepare data set for the output of the blur. And finally, we execute the convolution on our data set. This operator is overridden with MPI support and runs on all nodes in a cluster. Each node will process the part of the data set parallelly. And finally, when this completes, we will show the result to the user, or we can store the result to the disk. As you can see, there's no MPI-related functions or something like that. That's just script as we used to. This plugin makes parallel execution easier for biologists, but how it works under the hood. Fiji starts on some nodes in the cluster and executes same instructions. If the script uses our MPI-enabled operators, then are executed on different chunk. Otherwise, when we are not using MPI-enabled operators, then it's executed on a whole dataset redundantly, and calculation from that step will not gain any speed up, so this will be pretty useless and inefficient. So we need to use just MPI or MPI-enabled operators to run it on all nodes in a cluster. MPI-enabled operators uses our parallel operator, which makes the splitting and synchronization stuff more easier, and we don't have to repeat ourselves. The operator requires 2 parameters. The first one is output data set, which will be split, as you can see in the following slide, and a function that will be applied on each chunk. We will see this function in detail soon. So the output data set is split equally sized chunks. In this example, we have 9 planes and 8 nodes. So first node will process the first plane of the data set and the bit of the second plane. The second node will process the remaining part of this plane and a bit of this plane, and so on. So each node will have same amount of work to process. So it should take the same time to process then parallelly. But calculation may not take same time for all chunks. For example, elements around the boundary may require more time because of different code path, or there may be some condition that can make it took longer time. When we have split chunks into the nodes, then these chunks are split again into the sub-chunks and are processed parallelly by threads. For example, Salomon cluster that you were using during this workshop has 24 threads per node. Barbara, the Neuro 1 cluster, has 74 cores per node. So theoretically, we can gain 70 times speed up just from that single node. When we have 8 nodes, it's 8 times bigger speed up. But ideally, there can be some bottlenecks, as we will see later. So when we have our data set, it's split to the nodes and then again into the sub chunks, and in each this sub chunk is called this function. At first, we will get cursor to this beginning of each chunk. Then we need to get cursor in the input that data set. This is generic. We can take as many inputs we want. It's not limited with this operator. We just need to get this operator available in this scope, and then we can seek the disposition in this function. And then we need to iterate through each element in the chunk. So pick element by element and do some processing with it. In this example, we simply take element from the input and copy to the output, and then we need to move forward this cursor to the next element. When this completes in all threads, then the node is ready for synchronization. This result must be synchronized with each other node, so it can be used. So this result can be used as an input in the following operation. This is pretty hard and slow work because we need to copy this result to each other node. So first node must copy it to the second node, third, fourth, and so on. And this must be done with each node. We have made some measurements for 3.3 gigabyte data sets, and for example, when we run it on 4 nodes, then it took about 4 seconds. When we executed this on 32 nodes, then the synchronization process took about 8 seconds. This can take, sometimes it can take more time than the calculation itself. For example, addition is quite fast operator and may not gain any speed up when we use it across several nodes. In this last slide, we can see some pipeline of reference of Gaussians that uses some parallelized operators. So this first line in our script, and below the data set on all nodes in a cluster. In this example, we used 3 nodes. So the whole data set must be loaded into memory of each node. And when the loading is finished, then the node is waiting in the barrier for other nodes. when all nodes reaches this barrier, then then the calculation can continue with the next step. The next step makes the first Gaussian convolution. So basically we create a kernel, output data set, and the execute or parallel operator. So in this step, the data set is split to the chunks, then to the subchunks, and then the function is executed for each element on all nodes parallelly. And then this is finished, then it's synchronized to each other node. And then we can continue with the next step. That's this second Gaussian convolution, and this will be calculated in the same manner. So the output data set will be split, then executed on all nodes, and finally synchronized to each other node. Finally, these two convolutions are subtracted, the first one from the other, and saved to the result. This operator is also parallelized, but it may not be so take some. It may not take speed up benefits because this is quite an easy operator. But it depends on the size of the data set, the number of nodes we have, and the connectivity between the nodes. Finally, when we have this result, we can store it to the file system by the single node. The current drawback in this solution is that we are not able to process larger data set than we can store in memory of the node. So, for example, we can process 2 terabytes of data set because it can fit into the memory of the node. But it will be enhanced in the future with the lazy loading of the data set. So we don't need to load each plane of the data set into the memory, but we can use it on the first access to the plane. So for example, when the algorithm accesses this element, then the whole plane will be loaded into the memory or some chunks around it. So the another one problem is that synchronization. We can fix it by storing that result to the file system, and then when the following operation will need that result, it can load it again from the disk, but with lazy loading. And when we will make these two changes, it will be able to process more larger data sets that will not fit into the node's memory. Thank you for your attention. Do you have any questions?
Okay, so during the time, Stefanos has also prepared example how to run it into that HPC Workflow Manager. So basically, we will show you the other option that we have there. And after that, I will summarize both of them. So I will just ask Stefanos to run it quickly, just basically skip that not interesting part or part that we have covered several times, and just let's see how to run it, and then let's put it together.
Okay, so let's see the final example. Okay, first let's open the last worksheet from the main hub. It is the last link, and it is in the advanced section of the workshop, in the main hub. First, let's create a new folder. I will call this folder Peppers. Now, in the worksheet, click on the download peppers.tiff in order to get the standard test image of Peppers. And We will also need an empty script file, which we will call peppers.py, because this time we will be using a Python script. Make sure that the extension is py and not IJM. Now, once again, we're going to click Plugins, Macros, and Parallel Macro Client if you have closed this window. Otherwise, you don't need to do this. And right-click and create a new job. Here, make sure to select the script radio button from the job type section, since we are going to be using a Python script file instead of a macro file. Also select the Python file, the empty Python file we created in the peppers folder, and increase the number of nodes to 4. We're going to be using 4 nodes for this example. You could use more, but 4 are enough, and click create. And once you click create, the job will be created. Right click and press the open in editor. Now we will copy the code snippet from the worksheet, only code snippet here, and paste it inside the editor, and click on file save the file, and then once it is saved, we will close the editor. Now we can go back to HPC Workflow Manager and right click on it, and click on upload data. And once the data have been uploaded, which is the peppers and the script file, we can right click once again and start the job. And you can see now it is queued and creation time has been added. I will now fast forward the execution. Okay, now it's done. It has finished executing. So we can right click and download the results, just like in the macro type jobs and then we can right click and open the job subdirectory, and here we will see the results. Let's open the 2 images, the original one and the edge detected version that we created. So let's click File, Open, and then select the image from the working directory, from our working directory, and the job directory inside the working directory, in the local working directory. Click on Peppers, and this is the original image that you downloaded from the worksheet, standard image, and we will also open the Peppers edges, which is the edge detected version. As you can see the outlines of the objects of the peppers, and I would like now to thank you for participating in this workshop, and I would like to switch back to Michal.
Thank you. So basically, to sum it up, so today we have shown you the plugin that will enable you to run your macros and scripts on a cluster. The plugin is developed so that it should be easily to deploy it on any cluster. So basically we are here to help you. So after that session, I will also send you the contact. So if you plan to use this plugin on your installation, so we will help you with the installation. We will guide you how to do this. If you have some little bit different configuration of the cluster, so we can try to adapt it for you. So basically, thanks to this, you should be able to use it on your cluster, or if you have access to some of them, so on other installations. And based on what we have seen, so we have seen two options how to use it. One is more for the biologists or for the users of the Fiji who do not program, that basically use the functions which are there. So we have shown you how you can take your macros that you already have, and with small addition of the code that will basically split your jobs into a small groups, you should be able to divide it and run it on multiple nodes and get the results. And we have also shown you the other option. This is more for the programmers. So if you are intending to write your own scripts or own plugins, so then you will be happy that there is something like that Java Parallel Mpi that basically is able to split that data on the level of the data set. So you don't have to care about the files, but basically it divides the job. It's done this way that basically it works like a magic. So basically the same code you can run on a single computer, like on your desktop. And if you move that OpenMPI plugin to the cluster, then it will like a magic work parallelly, but not always, because we have parallelized only as part of the ops. So basically, if you are using these parallel ops, then it will work. If you are using the ops that basically are not covered by our implementation so far, so it will use the serial version. But thanks to it, you can basically parallelize even the code that already exists without the need to edit it. So I hope that you find it useful. And now we have the last 15 minutes for your questions. So feel free to ask whatever you need, or maybe try to describe what sort of job you are doing, and maybe we can help you to find out how to make it faster, smoother, or how to run it on a cluster. So feel free to talk. Okay, so I'm glad that you find it interesting. And as I said, so we will be, I guess, still available on GatherTown. So go there, and if you see us, so we can chat and discuss it. For sure, write your requests or your ideas on the Slack. So we will watch it after that conference. And as I said before, I will send you an additional email to all of the attendees, and I will put there also the contacts, so you can write me an email, and then we can just appoint some Zoom meeting and discuss it. So basically, we are looking for the users who are willing to parallelize the job, because basically our institution is not doing any sort of biological research. We just sit on a supercomputer, and we are looking for the users who would need and use the supercomputer for some good sort of the research. So our job is to basically make it possible and put the supercomputer into the use of, let's say, the science. Okay, so thanks all for attending. Feel free to put the comments and finish that questionnaires if you did not. And I hope that we will see on the social events, and after that we will not lose the contact, and we will keep in touch. So thanks again, and have a nice remaining of evening here in Europe.